Okay, so for today's lesson we're looking at distance time graphs. So we had an introduction to this last lesson, but distance time graphs and where they're useful. So first things first, what actually is it? So a distance time graph is a graph that helps show how an object or a body or whatever it is moving as time goes on, or how its distance that it's travelled changes with time. So let's do this as an example. Let's have a stretch of road. Beginning, we can have 0 meters, and halfway along is 10 meters away, and then 20 meters away. So if we were going to have someone moving along this and use a distance time graph, time's the thing that is changing, so we put that on the bottom. That's known as the independent variable, measured out in seconds. And then up the side, on the y-axis, we have the thing we're measuring, the outcome, which is the distance in meters. And as you can see from here, 0 meters at the start, and then 10 and 20 meters from there. Okay, so let's have a person, and then we can make them walk along the road. Start them off at 0 meters here. So if they walk nice and slowly along the road at a nice steady pace, and as you can see, as they walk along, their distance is increasing as time happens, and so we get a lovely, nice straight line graph showing how their distance has changed with time. So let's put the person back at the start again. Let's have them cover the same distance, but this time much faster. So they're going to be travelling at a faster speed. Now, as you know from the previous lessons, speed is distance over time. So the faster you're going, the more distance you cover in a small or shorter or even the same amount of time. So if I move the person more quickly along the line, along the road, then we'll see the graph and why it's different. So as you can see from this graph, the red line, they were moving much quicker, so they got to the 20 meters in a much shorter amount of time. So what we've got there is the straight line shows that they're travelling at a nice steady speed, and the steepness or the gradient of that line shows you whether it's faster or slower. So the steeper the line, the faster the speed. The shallower the line, the slower the speed. And we can go further. If we have some values on here for time, we can actually use this to work out how fast the person was actually going. So I'm going to add the values on the x-axis now. Okay, so there's our values on the bottom. So 0 seconds at the start, and then 2 seconds later, 4 seconds, 6 seconds, 8 seconds. So if we take the first journey where the person was walking quite slowly, the gradient or slope of this line is the same all the way along it because it is a straight line. And in maths lessons you've probably done calculating slopes and calculating gradients. However, in physics we can look at it in a slightly different way. So I'm going to use the highlighter pen to point out a couple of values on there. So we can, to work out the gradient, take any 2 points on the line and take readings from them. So because this line starts here at 0, 0, that's a nice easy point to start with. And then we're going to go along and we get to 20 meters. That took 8 seconds. So the next point we can use is 20 meters and 8 seconds. So what we have then, if we want to work out the gradient, when you're working out a gradient, you mathematically use the equation change in y divided by change in x, or sometimes it's shown as delta y over delta x, or sometimes delta y over delta x. Now, all that really means mathematically is how far up does it go from one point to the other, divided by how long did it take when it comes to speed and distance and time. So actually, all we're doing is going, how much has it gone up by? So the distance has gone from 0 to 20, so it ends at 20 meters, and it started at 0, so that's our top line, that's how much y has changed. And then x, time, well, it ended at 8 seconds, but it started at 0 seconds, so that bottom line is how much our time has changed. So 20 minus 0 for the top line. This is why it was nice to start at 0, 0, so it made life easier. That has changed by 20 meters. 8 seconds minus 0 seconds. Again, great that we had one of the points with 0 because it made life easier. Well, that's a difference or a change of 8 seconds. So 20 divided by 8 is 5/2, or 2.5, 2.5. And the units are there because we've got meters on the top, seconds underneath. So we've got 2.5 meters per second, or 2.5 meters per second. And that is the person's speed. Strictly speaking, it's their average speed, but because it's a lovely straight line, their speed hasn't changed, so the average speed and their actual speed all the way along are going to be exactly the same for the straight line, the black line there, for when they were walking. So just to re-emphasize that, we take 2 points on the line, and it can be anywhere. As long as the line's straight, you can choose any 2 points, so it's always best to choose points that line up nicely with values to make life easier. And to work out the slope or the gradient, you need to know how much the y value, that's the axis that goes at the side, has changed, and divide that by how much the x-axis value has changed. So we ended up at 20 meters and started at 0, so that's our top line, that's how much it's changed from 0 up to 20. We started at 0 seconds and ended up at 8 seconds, so it's gone 8 minus 0, so it's taken 8 seconds difference here. And that gives us our values or answers 20 meters change for the y-axis. And sometimes it's handy to draw that on. Delta y is 20 meters. And then we've got 8 seconds change for the bottom axis. Let's draw that on as well. Delta x equals 8 seconds. This notation you'll use more in maths as you move through the years. So for now, don't worry too much if that doesn't make sense using those symbols. It's just how much has each one changed. So 20 meters took 8 seconds, or 20 meters divided by 8 seconds gives us 2.5 meters per second, or 2.5 meters every second, and that is this person's speed along that slope there. So if we then compare that to their running speed, we do exactly the same process. I'll use a red pen to do the calculations for this one instead. So again, we choose 2 points. So the easiest thing to do, finished here at 20 meters, and that's at 4 seconds. And it started here at 0 meters at 0 seconds. So our y values have gone from 0 up to 20. So 20 minus 0 is 20. So we've got a change in y of 20. I'm just going to move that up slightly so I can fit that in. So delta y over delta x. So the change in y is 20 meters minus the 0 where it started. And that's going to give us a difference of 20 meters. So the person's gone the same 20 meters in effect. But this time, the red line starts at 0 seconds, but it reaches 20 meters in 4 seconds. So the difference between 0 and 4 is obviously 4. Again, if we do a slightly longer layout, we've got 4 seconds where we finished, minus the 0 seconds where we started. That gives us a difference of 4 seconds. So this time, we've got 20 meters took 4 seconds to travel. So we do that as a straightforward calculation. 20 divided by 4 is, of course, 5. And again, the units are there, meters on the top, seconds underneath, 5 meters per second. So what we can do now is we can compare those two lines. The walking speed for this person, that lovely, nice straight line there, we worked out was a walking speed of 2.5 meters per second, actually fairly fast walking speed. But then the red line here is steeper, so it's faster. And again, using the gradient, we worked out that that's actually a speed of 5 meters per second, which is a nice sort of jogging pace. Okay, so that was all quite straightforward. Let's move this up and look at another example. So this time, we'll have the road again as before. And we'll have the person walking on it again. Let's stick the person in there. Okay, so this time we're going to have it so they change their speed. So they start off walking really slowly, and then something happens and it causes them to run. So walking slowly, and then suddenly they speed up and they run. So what we've got here then, shallow slope where the person's walking slowly, steeper slope where the person is running and obviously therefore moving more quickly, and then the interesting point is this bit where it curves and changes from one to the other. So shallow slope, walking slowly, slower speed, steeper slope, obviously now going faster. The curve shows that the speed is changing. The word we use for changing, a change of speed, is accelerating if it's getting faster, decelerating if it's getting slower. When you get on to G to C, we don't use decelerating particularly, it's just accelerating against the motion. But for now, so because the curve is up, that shows the person's accelerating from their slower speed into their faster speed. You don't have to work out things to do with acceleration, you just have to recognise that's what the curve shows and state that. Okay, so let's just have one more go with the person on the graph. I'm going for a little walk. Okay, so this time the person's going to go on their journey and we'll talk through the graph as it's being produced. So here they are, walking away nice and happily, nice slow speed, they stop, something happens, and then they start to walk cautiously away and then run the rest of the journey. So again, as the graph was being drawn as the person walked, you saw that walking steadily away from their starting point, the flat line stopped because the distance hasn't changed but time's still going. Walking cautiously back, so this time the line goes down because they're getting closer to where they started. So that's a distance happening still, but it's in the opposite direction. And then the curve bit as they speed up, and then a really steep line back to the beginning as they run away. So the only extra thing new in there really, the flat line for stopped you've seen before, but if the line is going down, that means they're moving in the opposite direction to the way they were in the first place. And so even though it's a downward slope, that's still a shallow slope, so that first bit is walking back, and then it gets steeper as the curve as they accelerate, steeper slope as they run as fast as they can back towards where they started. Okay, so that's quite a lot to take in, so let's have a look at a couple of examples of the sorts of thing you'd be asked to do with the graphs. So I'm taking these from old sort of topic test questions and just taking out some of the words. So first example, you might get, for example, something saying sketch a graph for a bus journey where the bus is stopped, speeds up, then travels at a slow speed for a while, slows down and stops to pick up some passengers, then speeds up and travels more quickly on its onwards journey. So there's no values in here, so you can't be precise, so it's got to be a sketch graph. So when you see the word sketch, they just want you to show the right shape and have the layout correct. They're not interested in the values. So the question might go on and then say sketch a distance time graph. So distance, time, we haven't got any values for this. So initially the bus is stopped, so there must be a little flat line section. It then says that the bus speeds up and then travels at a slow speed, so we need it to curve upwards to show the speeding up, and then a straight line to show the steady slow speed. It's a slow speed, so it's not going to be too steep. So curving and then a line that's not too steep. Does that for a while, that's fine. It then tells us that the bus slows down, so we need the curve to flatten out a bit, and then after it slows down it stops again, so we need another flat part. So we're going to have a curve not upwards but downwards to show it slowing down, and then a flat line bit to show it stopped again. That's it picking up some passengers. It then says that the bus speeds up again and travels more quickly on its onwards journey. So we're going to have the bus accelerating up again, sloping upwards or curving upwards to show it's speeding up, and then more quickly than before, so a steeper line than before. So this line is the faster one, so that's steeper because it's faster. The blue line here is less steep, which means it's slower. We've got a nice flat bit there, so when it's flat that means it's stopped because it's flat. And then the same with the red bit here as well, that of course is flat, so that's stopped. I mean, another way of saying flat is that something has no gradient, because that's what it actually means. And so what we have then is a sketch graph showing the stages of the journey. The bus is stopped, it speeds up, there's the curve, travels at a slow speed, slows down, there's the curve the other way, stops, there's the flat bit, then speeds up, there's the curve up again to get it faster, and then travels on at a faster speed, so a steeper slope than we had before. And then they sometimes give you a question where they have the opposite, where they give you the graph and ask you to describe the journey. So let's look at an example of one of those. So let's say we've got distance against time, and let's say they give you a graph that does this. And they ask you to describe what's happening and maybe even come up with what might be going on. So the best thing to do is to look at the graph in sections. So the first bit is relatively steep. So again, I'll use the color code to, so first bit is quite steep. So starts off step 1, steady speed because it's a straight line. So we know that's a steady speed because it's a straight line initially. And we could say, got no numbers on here so we're not sure, but it looks quite fast, and we think that because it's quite steep. Then we have this bit where it curves, a long bit where it curves. So it's curving, and it's not curving up, it's curving in effect down. So that means we've got the long curve, so that means it's slowing down. We know it because it's a curve. That means it's speeding up or slowing down. The other way of looking at that is, as it's curving this way, the line is getting less steep as we go from the start of the curve, the steepest bit, to the end of the curve, the shallowest bit. So the fact that it's getting less steep as you go along the curve means it's slowing down. And then right at the end, we have this bit here where it's flat. So that means the person or whatever it is, it must be stopped, and we know that because it's flat. So you can make up a story there. It could be someone starts off running and then slowly gets out of breath and then has to have a stop for a rest, or some kind of story like that. Okay, quite a lot to take in there on graphs. They're much easier than they look, and by the time you've done a few, you get really used to them. You come back to this again in both years 9 and year 11, and you also do distance time graphs in maths as well at some point. So you'll have lots and lots of practice of using distance time graphs and what you have to do with them over and over again between now and obviously the end of your school and exams. So not too difficult, it's just practice.